Thanks for having me. My name is Tobias Stollenwerk. I'm leading the quantum computing group at the German Aerospace Center in Cologne. But soon, from August on, I will take a new position as a group leader at Research Center Jülich's Institute for Quantum Computing Analytics. This work was done in collaboration with Stuart Hatfield, who's working at NASA Quantum AI Lab. And I will talk about diagrammatic analysis for parameterized quantum circuits. So I will begin with a brief motivation, and then I'll introduce our extension to ZX diagrams to describe linear combinations of ZX diagrams as diagrams itself and related rules. And then I will briefly demonstrate this extension for the application to the analysis of parameterized quantum circuits. So why are we interested in parameterized quantum circuits? So this is an active research area with many open problems. It has a broad range of applications, from combinatorial optimization and machine learning to quantum chemistry and material simulation. Most basic research questions include, for example, what is the performance of a given ansatz for a given problem or a problem class, and how can we determine inexpensive or good parameters, or how can we select a best ansatz circuit for a given setting. The picture shows an example of a parameterized quantum circuits, which is QAOA, which stands for Quantum Approximate Optimization Algorithm. And this will be also our main example later on. Okay, so the goal, why we looked into this in the first place, was that we thought ZX calculus is a very interesting tool for us, which we wanted to investigate for the application that we are usually interested in, which are near-term quantum algorithms, such as parameterized quantum circuits. And but since we are new to the field, we are very happy to hear your feedback, so your feedback from the ZX experts on this. We are not the first who had this idea. For example, this paper here 2 years ago also looked into parameterized quantum circuits, but with a slightly different focus, and also other papers, of course. So let me briefly review ZX calculus. I don't want to introduce it here, just to make sure that the convention is set. So we use the gray and white spider convention. So the white spiders are Z spiders and the gray spiders are X spiders. And most importantly, we will keep the scalar factors, because this is really important for our application. For example, here in the C0 gate, we have this square root of 2 factor, if we write it as a ZX diagram. Here are the ZX rewrite rules given with factors. So we will make heavy use of, or for example, of the pi copy rule, where we have this e to the I alpha factor here, but also the factors appear in other rules. So now I will come to our extension. So imagine you have a linear combination of 2 ZX diagrams, which is shown here on the left-hand side. So you have a diagram on the left with m inputs and n outputs labeled with A, and another diagram B with the same number of inputs and the same number of outputs as diagram A. And then you also have 2 factors, the factor B and the factor A. And we introduced a new kind of diagram which describes this linear combination. And we did that by introducing this new symbol, sigma here, which makes it possible to branch off both contributions in this case for the linear combination, and each contribution is then written inside such a bubble, and the bubble is connected to this new symbol, and we write the factors on the connection between the bubble and the new symbol. I was made aware of that similar or related work was also done in this paper here. I didn't have a chance to look into it closely yet, but it seems that there are some relations there. Okay, so it turns out that we need two rules with these new diagrams. And I forgot to say, of course, this isn't just an example for two, the sum of two terms, but the extension to more terms is straightforward, of course. And here I'll show the first of two important rules which are needed to handle these linear combination diagrams. The first one is the diagram pull rule. So on the left-hand side, you see a ZX diagram where part of the diagram, the lower part here, is a linear combination. And so what you can do then is to pull in and pull out outer parts into these bubbles and vice versa. So on the right-hand side, you see that we pulled all the surrounding of this linear combination diagram into these bubbles. And of course, we can do it backwards, and we will make heavy use of that later on. What is also worth mentioning here is this of course also holds if we don't have any inputs, so if L is 0, or we don't have any outputs if K is 0, or we don't have any connections if P is 0. And the second rule we need is the product or composition rule for linear combinations. So here we have the product, or meaning that we apply these two diagrams one after another, and each of the diagrams is comprised of of the linear combination of two terms. So here we have M inputs and N outputs, and then after that, the diagram with N inputs and L outputs is applied. And this behaves as you would expect. So when we have the product of two sums with two terms each, we get a sum with 4 terms. So we get this contribution AC, AD, BC, and BD. And the corresponding factors AC, AD, BC, and BD. As I said, these are the two rules we actually need to meet our purpose, but sometimes it's convenient to have additional rules. For example, it shouldn't matter if you write the scalars on the left-hand side of the bubble or on the right-hand side of the bubble. So we can just pull these scalars through the bubble. And another thing is that if you don't have any inputs, so if you have states, which is shown here on the left-hand side, then you can actually cut one part of this branching diagram. And just are left with this one here, which is just shorter, I guess, and sometimes more convenient. And the same holds true for effects. So if you don't have any outputs, as it is shown here, you can cut the right-hand side of the diagram, and you are left with something like this. And finally, we could also write this linear combination diagram completely without these bubbles. So we would directly connect here these M inputs via M wires to the m inputs of the A diagram, and then the n outputs of the A diagram to this symbol here again, and the same for B. However, we will not make use of this notation in the talk, and also not in the preprint paper. Okay, so let's go to an example. So here we have a single qubit Z rotation, and it is well known that you can write it as a linear combination of an identity with a factor of cosine, and a Pauli Z with a factor of I times sine. We will always use this shorthand notation in this talk. So whenever you see a C, it's a cosine, and whenever you see an S, it's a sine. And of course, this single qubit rotation is related to a Z spider via an affine transformation. And since we know what the linear combination is, we can directly write this as a linear combination diagram. So we get the cosine times an identity plus I times a sine times a pi Z spider. And the same thing, of course, can be done for the X rotation. It looks the same. You get a cosine times the identity and a sine times an X pi spider. We can get a little bit more complicated, and this is a very common factor in parameterized quantum circuits, for example, in QAOA. So we have these two qubit rotations, and we can also write that as a phase, so-called phase gadget, which looks like that. In contrast to most works on phase gadgets, here we have this factor, which I said is important for our application. And because the product of two ZZ Paulis is equal to the identity, we know that, again, we can write this as a cosine times the identity plus a sine times two pi Z spiders. So we get a diagram like that for these linear combinations. And again, we will make heavy use of that later on. Okay, so with this, I want to come to the demonstration of how we can apply these extensions to linear combination diagrams for the analysis of parameterized quantum circuits. So first of all, here we will look at the QAOA algorithm, which stands for, as I said, quantum approximate optimization algorithm. And we will apply this algorithm for the MaxCut problem on this simple graph. I want to stress out that this quantum approach is aiming to find approximate solutions to the MaxCut problem. So we will basically use this parameterized quantum circuits to get candidate solutions, so to sample from the low-lying energy space of the spectrum. And then it can be important to look at the expectation value of this quantum circuit in order to assess the performance of the algorithm. For example, to investigate bounds for the algorithm. So that's basically the background why we want to look into that. So now I come back to the actual example. So in the MaxCut problem, you want to divide or cut the edges of a graph in such a way that you maximize the number of cuts, which basically means you divide the nodes into two partitions. And then whenever you have an edge which connects two nodes from different partitions, you you count this, and you want as many counts as possible. And this is what this cost function can then be written as a Hamiltonian, which is shown here. So each node now corresponds to a Pauli Z operator. And when you have the solution and the eigenvalue is +1, then this node belongs to the one partition, and if it's -1, it belongs to the other partition. And you can see then whenever you get two different values here, so you have, for example, +1 and -1, you get a negative contribution here, and so the whole thing adds up. And in the end, you want to minimize this cost function, or to find the ground state of this cost function Hamiltonian. And in order to do that, you, as I said, apply the QAOA algorithm, and this works as follows. So now I will explain how this circuit here is comprised. So you start with an initial state, which in the standard QAOA setting is just the plus state. And then you apply alternatingly different layers. The first layer is just the exponential of some parameters, gamma 0 times the cost function. And so this is called the phase separation layer. And then you also have another type of layer, which is called the mixing layer. And again, in the original setting of QAOA, this is just sum over all X Paulis. And in QAOA, you can repeat this pattern as long as you want, and the number of layers is then a parameter of the approach, which we usually write as QAA minus P, where P is the number of layers here of the same kind. But for this demonstration, I will restrict to P equals 1. So we only have one layer of each type, which is shown here. So you get a quantum state which depends on just two parameters instead of two P parameters in the general setting. And you have the initial state, and then you apply the cost function Hamiltonian or phase separation layer, and then the mixing layer. So, and what we want to look into is the expectation value. As I said, it can be important to get an analytical formula for your expectation value. And this is what we are going to do now with the X calculus. So the expectation value is just shown here. So if you apply this quantum state from the left and the right to this Hamiltonian, you get something like this, which is comprised of a sum over expectation values of ZZ terms. So let's look into that. So as I said, we have a lot of these ZZ terms, and we will now look at a single one of them, which in this case is just Z2, Z3. And here you can see this expectation value written as a ZX diagram. So on the left, you have the plus states, and on the right, you have the plus effects. And then you have the phase separation layer, which is comprised of these phase gadgets. And you can nicely see the original graph structure here represented again in this phase separation layer. And then you apply the mixing layer, which is just single qubit with X rotations here. And this is the left part of your bracket, so to say. And in the middle, you have the Z2, Z3. So you have just Z pi spiders, and then the conjugate of the state on the right-hand side. And yeah, so our goal is now to just contract the whole diagram in order to get an analytical formula for that. And it turns out that this is necessary to use our extension to ZX in order to do that nicely. Okay, so let's dive into it. So what we want to do actually is to pull all the gray X spiders to one side and all the white Z spiders to the other side. And we want to now pull the gray spiders to the right and the white spiders to the left. So first we apply the pi copy rule to pull these two pi's here, Z pi's, to the left, and then also recombine the X spiders to make things a little bit more easy. So you get something like this. Here you get these terms. Of course, they are not important if they're globally, but here in our case, remember, we have a sum over all these things. So they are important here. So now we have achieved what we want. So the white spiders are on the left. And now, in order to proceed, it's really difficult to get out of these phase gadgets here, because we don't have a pi spider or something in here. We have something which is just an arbitrary angle. And here our extension helps. So now we will replace both of these general angle X spiders with something simpler in a sense. Of course, it also makes things more difficult, but we will see that we can achieve our goal here. So we replace that with this linear combination diagram, and we will get something like this. So we have these two linear combinations now in the diagram, and but it turns out that it will be easier to have just one linear combination diagram. So what we do is we apply this product rule, because you can see both of these things as a product. And then we apply this product rule and get a linear combination with 4 contributions. And of course, why we are doing this? Because now we only have pi spiders in here, pi spiders or identities. We don't, and all these ugly arbitrary angles are in the factors. So, and then we can actually use the diagram pull rule to pull all the outside surroundings of the linear combination diagram into each of the bubbles. So now we have something where we have 4 different contributions with various factors. And now we can go on by just looking at each of them individually. And as an example, I'll just choose this second term where we have the identity and a pi spider. So let's look at that. So again, we use the same strategy. We want to pull all the gray spiders to the right. So I use the pi copy rule to pull the spiders in here. And then I change the form a little bit and I get something like this. So here I have a phase gadget and the conjugate of the phase gadgets on the other side, and the same here. And this is just cancels each other out. So I get something like this. And now I have a phase gadget here and almost the conjugate of the phase gadget, but with a pi spider here. And this is also very common. So let's change the form a little bit. And then we can just use standard ZX calculus to derive this very useful formula. So you have these 2 phase gadgets with different numbers of X pi spiders in it. So these T, R, B, and L are just Booleans, so they can be 0 or 1. And depending if the number of pi x spiders is even or odd, you either get a phase gadget again, or you get something disentangled. So in our case, we only have one x pi spider in this diagram, so we get a phase gadget. So this is the phase gadget again, and in order to proceed now, we have to again resort to the linear combination of this phase gadget, and we saw how this is done earlier. So these phase gadgets can be written as a linear combination. So I do that. I replace both phase gadgets with these linear combination diagrams, and then I apply the rules that I laid out before. So in particular, the diagram pull rule. So I can pull in these states and effects here, and I get something like this. And now I can, now I can actually see directly, if I would apply this diagram pull rule again, which factors will, not factors, which contributions will to the sum will survive. So for example, here, if you combine both top bubbles, you see that you get in the middle something which is a pi on the left and a 0 on the right. So this is because it's orthogonal, this is 0. And the same holds true if you look at both bottom bubbles. The only thing that will survive is you take the bottom bubble of the left and the top bubble of the right, and then you combine it and you get something like this. And yeah, then you can go on. So this is straightforward, and you will end up with the final result for this particular contribution. So, and we can do the same for all the other 3 contributions. Remember that we had these 4 contributions, and I just showed you the calculation for the second one, and the third, fourth, and first one can be done accordingly. I have to say that this particular example is actually more complicated than the general case, because you really look at each contribution individually, but in the general case, you can make more general assumptions, which actually make things easier. But I refer you to the paper, the preprint paper for that. So in the end, we will end up with the end result. And of course, we actually would need to do this for all the other contributions. But as I said, the general case is actually easier. This was more a toy problem just to show you how things work. So let me summarize. So we have extended the ZX calculus towards linear combination diagrams for the analysis of parameterized quantum circuits. And our main application there was the analysis of expectation values of parameterized quantum circuits, in particular QAOA. In the preprint paper, we also show various other applications. For example, single qubit rotation ansatz, hardware efficient ansatz. On the bottom right here, you can see QAOA with level 2 on a ring. So you can very nicely see this so-called light cone rule, which is the result of the locality here. And as I said, we also reproduced the results of Fari and Wang in another paper for the general QAOA1 case with the ZX calculus. And future and related work. So of course, we would like to further investigate to what degree diagrammatic methods can help in resolving the many open problems we have in parameterized quantum circuits. For example, we could look at computing gradients or parameter settings. We could also go to applications beyond combinatorial optimization, for example, quantum chemistry. It would be also very interesting to combine our results with recent work, which is very related. For example, the paper of Wang or Jean Del, which came out in the last 2 months. Yeah, and we would also like to investigate if diagrammatic approaches can help us in designing new improved ansätze for parameterized quantum circuits. Thank you.